angular displacement for a particle performing a circular motion. Here we can draw a circle. Now suppose here is a point P. A particle move from the point P to the point Q. Now draw the position vector R1 from the center, and the point P is moved to the point Q, another point, along the circumference. So it is in the circular motion. So another point here, the position vector is R2, which makes an angle theta. This angle theta is known as angular displacement, and the unit of angular displacement is measured in radians, not in degree, and we can find its direction of angular displacement since it is a vector quantity for a small displacement. So it is given by a right hand rule. We can find the direction of angular displacement. So what are we going to do? Just you have to see the direction of rotation, and this is the axis of rotation. Now you have to curl the axis of rotation in this way. The four fingers are wound around the axis of rotation, and this outstretched thumb finger points the direction of angular displacement. If this is the direction of rotation, you have to grab the four fingers around the axis of rotation and stretch the thumb, which gives you the direction of angular displacement. If it is the counterclockwise, angular displacement is positive. If it is clockwise, the angular displacement is negative. Positive for counterclockwise, anticlockwise, and negative for clockwise. And here for the negative, the direction of angular displacement is downwards according to right hand thumb rule. And here we have the vector relation between linear and angular displacement. So now we are going to make a relation between the linear and angular displacement. We can draw a circle, and here the point P, and here is the point Q. So here is the center, and we draw the position vector R. Here is another position vector R. Here is R1, R2. Here it makes a small angle. We can make a d theta, and it moves some distance here. So we can say a small distance dr. Now we can make a vector relation. In mathematics, if the point from the point P to Q is known as arc length. If this angle is very small, this angle, the sweeping angle is very small, this arc length will be known as a straight line. We can assume as a straight line. If it is really very small length, it becomes a straight line. So if it is a straight line, then it is the distance covered during the given time. So in speed formula we know the speed formula is distance divided by time. So the distance covered during the time, the given time is how much? dr, right? So if I want to find the arc length, the formula is we have to multiply the angle and the radius. So that is the arc length formula. L is equal to theta multiplied by r. This L is the arc length. So here we have taken the arc length as dr, as we are deriving the vector relation between linear and angular displacement. We are assuming this a small curved path, arc, has a straight line. So the dr will be equal to angle multiplied by the radius of the circle. Angle multiplied by radius of the circle, we can find the arc length. So here this arc length becomes a linear displacement, as we are assuming the angle between the position vector is too small, then the arc length will become a straight line, become a linear displacement, will be a straight line motion like a point P and point Q. This motion is known as linear displacement. So the linear displacement is here dr. If you want to find the linear displacement, you have to multiply the angle, a small angle changed, and multiply by the position vector or the radius vector. So this angular displacement is a vector quantity. So d vector, this is the vector relation between linear and angular displacement. Angular velocity, the rate of change of angular displacement, like a velocity, a linear velocity. How we describe velocity? It is a rate of change of displacement. In the angular velocity, the same way we say rate of change of angular displacement. In the linear motion, we say angular, just a displacement, rate of displacement. Here we say rate of angular displacement, just we have to include the word angular displacement, right? Okay, and it is denoted with the letter omega. Omega, it is the symbol for angular velocity. In the same way, if this is a plane and a vertical line passing through the plane is known as an axis, and if it is counterclockwise, the disk is rotating in a counterclockwise, the direction we can find using right hand thumb rule will be outward, and it is the positive direction, right? So same way, same as like the angular displacement, the direction we can find using right hand thumb rule for the angular velocity. And here the SI unit of angular velocity is radian per second. Radian per second. So we write like this, radian per second. So here we should not write like that because it is not allowed in the SI units. Radian second, and the first letter should be simple R. Radian. We should not write radian per second also. This is also wrong. Radian per second. Okay. And here we have a derivation for angular velocity. So angular velocity is also a vector quantity, and it is the rate of change of angular displacement. Rate means divided by dt or divided by time. divided by time is a rate of change of, so another d, this d denotes change of angular displacement. So change of angular displacement can be written like this. What is the change? Theta 1 theta 0 divided by dt. So what is theta 1? Final position. Theta 0 initial position. So if I want to find the change, always we subtract the final minus initial, right? So in another way, if I want to find the angular velocity, that means the angular displacement divided by time. What is angular displacement for one complete revolution? Suppose the point starts from the point P and ends to the same point P. So the total path covered by a particle is one complete circle, one complete revolution. In one complete revolution is 360 degree. 360 degree. So if you multiply with 2 pi divided by 360, you will get your answer in radians. So 2 pi radian. So multiply 2 pi by 3 divided by 360 is the value to convert from degree to radian. So what is the total displacement, angular displacement? 2 pi radian divided by the time taken for one complete revolution is time period. So we write capital T. Simple T just a time taken. Capital T is the time period. Time period means time taken for one complete revolution, one complete rotation, one complete wave, one complete vibration, oscillation. These are all called time period, right? Okay. And if we want to change, this is the radian revolution per minute. Now we can change revolution per minute to revolution per second. For example, now 2 pi capital N divided by 60, it will become 2 pi n. So what is capital N? Angular speed in revolution per minute. What is simple N? Revolution per second. If you divide the revolution per minute by 60, you will get your answer revolution per second. The revolution per second is otherwise called hertz. Hertz is the unit of frequency. Frequency, number of rotation formed in 1 second, number of revolution formed in 1 second is known as frequency. Number of waves formed in 1 second, number of vibration per second, number of oscillation per second, these are all called frequency. And frequency is equal to 1 over time period. This is the relation for the time period, and frequency is always inversely proportional. Time period is equal to 1 over frequency, just inversely proportional to each other. And what is here the simple T? Just time taken, capital T, time period. So this is the main formula. W is equal to 2 pi divided by T, or 2 pi frequency F. Omega is equal to 2 pi frequency. Omega is equal to 2 pi divided by time. You know this 1 divided by time is frequency. That's what it is written like this here. So another formula is here. rate of change of angular displacement. Here is the first equation and second equation and third equation. And the same way we can find the direction of angular velocity using right hand thumb rule. Now here next we need to know angular speed. Angular speed is the magnitude of angular velocity. Magnitude. If you find the magnitude of angular velocity will give the angular speed. Here we have an example to be more clear. If we draw a circle and take 3 points on the circle, here is a point P and here is a point Q and at the bottom is a point R. Now we can draw the tangent at the point P, at the point Q, at the point R. So here are the tangents. So we know this tangent is a instantaneous velocity. Here v1, here v2, v3. Instantaneous velocity or tangential velocity. And it is the center. From the center a line drawn, this is the position vector, and here is the another position vector r2, and here is another position vector r3. And this also we have learned the tangential or instantaneous velocity will make 90° to the position vector or radius vector. Okay, so these are all vector quantities. Now if it is the uniform circular motion, if the object is moving, here the object is moving in a circular path, if this motion is uniform circular motion, then the magnitude of v1 vector is equal to magnitude of v2 vector, and magnitude of v2 vector, v3 vector is equal, will be equal magnitude. But the direction of v1 is not equal to v2, is not equal to v3 in the uniform circular motion. If it is non-uniform circular motion, if it is non-uniform circular motion, the velocity magnitude of velocity v1, v2 is not equal to v3, v1 is not equal to v2, is not equal to v3. What about the direction? Direction of v1 is not equal to v2, is not equal to v3. So in the non-uniform circular motion, magnitude and direction are not equal to each other. And here we have the linear relation between the angular speed, angular velocity and linear velocity. The relation is v is equal to r omega. Here the v is a linear velocity, r is the position vector or the radius vector, and omega is the angular speed or angular velocity. Is a relation. Angular acceleration, the average angular acceleration is defined as the rate of change of angular velocity. Same in the linear acceleration, the acceleration we say rate of change of velocity. Here the change of velocity we say change of rate of change of angular velocity. So the unit of angular acceleration is radian per second square. Same here, meter per second square in the linear. So the meter here becomes radian. In a circular path, it becomes radian and second square. And here the symbol for angular acceleration is alpha. Like a ribbon, alpha is equal to rate of change of, this is the rate of, dt is the rate of, and this is change of angular velocity. So alpha we can write change in velocity is final velocity minus initial angular velocity divided by the time taken. This is a formula. The direction of angular acceleration is given by the right hand thumb rule, right? If the angular velocity is increasing, then the angular acceleration has the same direction as that of angular velocity, that is positive. If the angular velocity decreases, then the angular acceleration is opposite direction of angular velocity, it is negative. If angular velocity decreases, angular acceleration is negative. Angular velocity increases, angular acceleration is positive. For the uniform circular motion, angular acceleration is 0. So here there are three: positive, negative, 0. Angular acceleration is positive when the angular velocity increases. Angular acceleration is negative when the angular velocity decreases, and when the angular velocity is not changing, constant for the uniform circular motion, angular acceleration is 0. Now we can derive the period of revolution. The period of revolution period is denoted as t. In the linear motion, the time formula is distance divided by speed. The same in the circular motion, the period time taken for one complete revolution, right? So time period is equal to one complete revolution divided by the speed, linear speed. So here one revolution is 2 pi r. It is the formula of circumference of a circle divided by the linear speed is v. This is the formula, time period formula. And we have another relation for linear speed. V is equal to r omega, relation between the linear and the angular velocity, linear velocity, angular velocity formula. So you can substitute here. So this will become like t is equal to 2 pi r divided by r omega. Here you can cancel radius. So the final formula 2 pi by omega. So you can use these three formulas for calculation. Depends on the given values. Here two formulas. We have two formulas: 2 pi r divided by linear velocity, or 2 pi by omega. Then another one, the next we have the another formula, that is t is equal to 1 over frequency. So if you want to find the frequency here, you have to take the reciprocal. So if you take the reciprocal, 1 over t is equal to omega over 2 pi. So this 1 over time period is frequency, because frequency is equal to the inversely proportional relation. 1 over time period is equal to omega divided by 2 pi. So if you find time period, for example, the time period of a revolution is 5 seconds. So if you want to find the frequency, you write this formula: 1 divided by 5 is equal to 0.2. The unit of frequency is hertz. Unit of time period is seconds. Unit of time period seconds. Okay. Next we have a derivation, a small derivation expression for angular acceleration. Expression. Angular acceleration, that is alpha. You know the linear acceleration formula is dv by dt, and in the angular, this linear to angular, if you want to change, it will be d by dt, the linear velocity angular velocity relation r omega, because v is equal to r omega, linear velocity angular velocity relation. And here you can take r outside and you multiply d omega by dt. This is rate of change of angular velocity is alpha, angular acceleration. So this is the relation between linear acceleration and the angular acceleration. Here r is the radius of the circular path, is always constant, right? And here the omega is the angular velocity, alpha is the angular acceleration, simple a is the linear acceleration. Okay, so in the next class, in the next video, we will be discussing about numerical problems on circular motion. So it will be interesting. Please keep watching my videos. Thank you very much.